Hello, this is Nachum Danzig. I'm a teacher at the Jerusalem College of Technology, and today we are discussing the single cycle in the MIPS architecture, and particularly I want to discuss how the controller in the single cycle generates the correct signals based on the opcode that is given. So, for example, here, as you see, are the control line settings for various commands, like any R format should have these lines lit up as 1 and these as 0. So in other words, the register destination should be 1 for the R format. And similarly, load word should have these ones lit up, the store word and the BEQ. In other words, these are the output lines as they should be generated by the controller. Now, how are we going to do that based on the opcode that we're given? So we're going to do that in logic, using logic gates. And it's really quite straightforward. In other words, we don't have to like have some big table that we say these lines if it's this, and we don't have to have some big else. We're going to do it all with logic codes, with logic gates. So here is the design of the controller for the MIPS architecture. And you see here, for example, the opcode for an R type is 0, which would be represented as 6 zeros. And here's the opcode for load word 35, which would be represented by 100011, etc. So store word would be 43, and BQ would be 4, which are represented this way. So those are the lines that are going to come into the controller as these lines here, op 0 through 5. 0 being the lowest number, so that would be the rightmost number. Like, let's say on a load word, it would be this 1. And then 1 would be the next one. And then op 2 would be the 0. Op 3 would be the next 0. Op 4. And finally, op 5 would be this last 1 over here. So those would be the lines as it'd be assigned based on the opcode. The opcode, in other words, is read from the memory. We put it into the instruction register. And those lines are direct, or if there is an instruction in the single cycle, there is no instruction register, but those lines will go directly into the controller, and we'll have ones and zeros on these lines. And they'll have a certain effect on these logic gates, and these are the output lines that need to be lit up or not lit up depending on what the command is. So let's see how it works. So for example, here are the input lines of an R type. R type is all zeros, so I put all zeros on these lines. Now, if we go through, we'll see that since all of these lines are coming into this AND gate, I have this little circle here. The circle means inverted. So they're inverted, so that means they all become 1s. So these are all 1s, so we're going to get a 1 on this line, and hence I wrote a 1 over here. Here we see that we have a 0 because some are inverted, but some are not. So that's already going to tell us it's be a 1. This is an AND. And also here some are inverted and some are not, so it'll be 1. And here all of them are inverted except for 1, so that's also not going to be the AND is going to produce me a result of 0. Because in other words, the only time I'll get a result of 1 is when they're all 1s, because it's an AND. So then I have on these lines 1, 0, 0, and 0. That will produce me, hopefully, well, this is what it should produce me, which is for an R type, it should be 1, and then 1, and then 1. Let's see if it does. Notice that there's a 1, 0, 0, 1. That's exactly what we saw over here. 1, 0, 0, 1, 0, 0, 0, 1, 0. So that's the R format that it's supposed to produce. Let's go back to that picture, and let's see if it does. So, this is rather straightforward. You see there's a 1 on this line, so this line comes all the way out here, so it's going to be a 1. This line is a 0, but it's going into an OR. So if there's a 1 on the next line, it'll be a 1, but it's not. They're both zeros, so 2, 0, or 0 is going to be 0. This line is straight, that line, so it's a 0. This line is that 1 coming in here into an OR. Well, once we have it's at least one of the input lines to an OR is a 1, we're going to get a 1 over here. So that's what we wanted. This 0 is going to come straight through to here, so it's a 0. This 0 is going to come straight through to here. This 0 is going to come straight down to here, and also this 0 will come down to the ALU op 0. But what do ALU op 1? Well, that comes from the first line, so that's a 1. So we got exactly the control signals that we wanted based on the opcode of 0 for all the R types. Let's do another example. Just a second. Oh yeah, sorry, I was there. Here, load word. A load word is a 35, so that's 10011. So here we have 100011, and that's going to generate a 0 over here. Why? Because, well, this one, the first one, for example, is inverted. So the highest, I don't know, the leftmost digit is inverted, and if it's a 1, that means it's a 0, so it produces a 0. What about this one? This is going to be a 1, because if you notice, uh, they're not, the first one's not inverted, and neither are the last two, which is exactly what I have 1, and these ones go straight through, but the three middle ones here are inverted, and those correspond to these three zeros. So this will be all 1s. So now we have 0, 1, and then 0 over here, well, those three middle ones, notice that they're all here. They're all zeros, but only one. But here, one of them is not inverted, so that'll give me a 0. And also here, I have inverted. Let's say, for example, the first one, which gives me a 0, which is on an and, it's going to give me a 0. So I'm definitely going to get 0, 1, 0, 0, and then that is going to give me a 0 on this line. The 1 coming through here into an OR is going to guarantee me a 1. The 1 also goes straight through to here. That's going to give me a 1. The 1 also goes to this OR, that's going to give me a 1. And the 1 also goes to this, and it gives me a 1. So that gives me all these 1s. And the rest are going to be 0, 0 from this last one is going to come into branch. And ALU op operation 0 will be 0 because this one. What about ALU operation 1? Well, that's from the first one, and that's also 0. So we're going to get exactly this output, which is what we wanted. Let's do another example. That's load word. Let's do store word. So store word is 43. If you notice, the load word and the store word are very similar. The only difference is this 1 here in the middle. And also notice it's quite interesting because notice that the 1 was here. In other words, on the R type there was a 1 here and the rest were zeros. Then the 1 sort of moved down one space, and now the 1 moved down another space. It's kind of interesting. So that's the store word is 43. So notice you may have wondered why, load word and store word are why isn't 135 136? Well, that would be in a sense they are right next to each other because it's just one digit different. The load word and the store word are exactly the same binary except for this one digit, and that's going to be relevant over here because there's a 1 over here. So this is going to be a 0 because, for example, the first one is a 1, but it's inverted, so that gives me a 0, and a 0 on an and is going to be a 0. And the third, well, I mean, we can take, for example, this 1 over here, op3, opcode line 3 is going to get inverted, and it was a 1, so it becomes a 0. So that makes this a 0. But look over here on this one, the two that happen to be 0, which is opcode 4 and opcode 2, are the exact two over here that are inverted. So that means this will all be 1, so I'll get a 1 over here. Now over here, it's, as soon as opcode 4 comes in, well, opcode 5 comes in, and it's a 1, it gets inverted to be a 0, so this and will be a 0. So that will definitely give us 0, 0, 1, 0. And now, on this line, we'll get a 0, which is, don't care, so a 0 is also fine. Here, there has to be a 1. Well, this is a 0 coming to this OR, but the second one coming to the OR is a 1, so that gives us a 1. The next one is a don't care, so we'll skip that. Doesn't matter. Register write, as long as both of these have to be 0. Well, it's the first and the second, and they're both 0. Mem read is also 0. Mem write is exactly the third one, and that's going to be a 1, which is what it should be. And now the fourth one will be branch and ALU op 0, which are both 0. And ALU op 1 is the first one, which is also 0. So we get exactly that code. And last but not least, let's look at a BEQ. BEQ is all zeros except for opcode line 2. So since these are all inverted, the one single one that's a 1 will turn into a 0. That will make this a 0. This will become 0 also because, for example, the first line is not inverted and it's a 0, so that's a 0 over here. And again, same thing here. The first line, the op3, and when I say first, I really mean the highest, the most significant bit. That's opcode 5 is a 0, and it's also coming in here, and that's going to make this AND a 0. But over here, notice that in this AND gate, everything is inverted. That's all these zeros except for opcode 2, which is a 1. And notice that that's exactly the one that comes to this line that's not inverted. So it ends up that all the zeros are inverted to 1s, but the 1 is the one that's allowed to go through. So all of these are 1s, and therefore this AND will give me a 1. So that'll give me on the ALU source, well, this line coming in, both lines, these two lines are both zeros, so this OR will be a 0. I'm skipping the don't care ones. Over here also, the first AND gate produces 0, and the second AND gate produces 0. Those are the inputs for this OR. So there's both zeros, so it's going to be 0. And that's also the same output is the memread. Memwrite is the third AND gate, and that's going to be a 0. But the branch, which is what this is actually, is going to be dafka. This is going to be precisely this fourth gate. It's going to come straight through, and that's our branch 1. And that also affects the ALU operation 0, which will be a 1, which is what we wanted. And ALU operation 1 will be a 0 because it's from the first gate. So we see that using these logic gates, we have gotten the exact results that we needed based on the opcode. The controller has produced the results we wanted. So that shows us how the inner workings of the controller produces based on the actual values of the opcode, the control lines that we need to be set for the single cycle data path. Okay, that is an explanation that should be sufficient for you to understand how the controller works. If you want to know how the ALU controller works, well, it works in a similar fashion with logic gates. I'm not going to go through it, but you can imagine that it also has inputs and also has outputs. We can obviously make logic gates for it. You can use logic gates to create the desired outputs. Okay, thank you very much. I hope this helped. See you in the next video.